This mini lecture is on the naming of alkanes, but first of all we're going to go from how to draw alkanes, going from the name to the structure. You'll find most of this information in your class handout. This is on page 20. Now the first thing we want to do is we want to look at the name and we look at the end. And the end of the name has what we call the base chain. This makes up the central part of the compound. These are a list of the base chains that I want you to know. How long they are, how many carbons they are. Methane, ethane, propane and butane are a little bit hard to remember because they don't really have any link to anything you've seen in the past, but those are 1, 2 and 3, 4 respectively. The other ones you would be familiar with, like pentane, 5 like pentagon, hexane 6 like heptagon, hexagon, heptane 7 like heptathlon, 7 events, octane 8 like octopus, 8 legs, nonane 9 like a nonagon, decane 10 like decade. Now you know I haven't used line structures here, but you'll be required to use line structures, so let me do the same thing as I'm doing here, but I'll do it for line structures. Alright, so we've got heptane. That means that we're looking at 7. So 1, 2, 3, 4, 5, 6, 7. Now the other parts of the name, 3-methyl, 4N-propyl, tell you what's joined on to the base chain. But we've got to figure out where those things are joined. So what we do is we number the chain, and we number the chain from one end to the other. Now we know where the groups are attached. So what it says is we have a methyl group attached to 3. So let's look at the substituent groups that we're going to be using. The substituent groups you'll be talking about will be these here. You've got methyl, which is 1. Now you'll notice that 1 carbon methyl comes from methane. Now methyl is different to methane because it's a group. It's methane is CH4, methyl is a CH3 group. So they're different. CH3 is different to CH4 because there's a point where it can attach to something. And that's what we mean by a substituent group. CH4 can't attach to anything. CH3 can because there's a vacant space. So all of these all have a vacant space at which they can attach to something. A base chain in our cases. Ethyl comes from ethane. There you go, ethyl group. 3 carbons. Now with 3 carbons something interesting happens. We begin to see 2 possible points of attachment on a 3 carbon chain. We can either attach it at the end, CH2, CH2, CH3, or we can attach it off the middle carbon and we can have CH with 2 CH3s attached to it. So just showing you an example of that. Alright, and there's the attachment point right there, and that can attach to anything. And that's obviously different from this situation. Where you're attaching the group off the end carbon. With 4 carbons, there are 4 different kinds of ways that those groups can be joined together. You've got butyl, you've got sec-butyl, you've got isobutyl, and you've got tert-butyl. It's probably easier to show these as line structures, and here are line structures for all of those groups. This dotted line here represents the base chain, so these are all joined to a base chain. Now notice that the carbon that's part of the base chain is not part of the group, so it's just joined to a carbon on the base chain. So butyl, or N-butyl, would be 4 carbons in a row off the base chain. Sec-butyl. You can remember that it's attached to the second carbon, sec-butyl. Isobutyl kind of looks like a Y shape. I kind of remember that by saying Y-sobutyl. Y-sobutyl, isobutyl. 1, 2, 3, 4. And you've got tert-butyl, which looks a lot like the letter T. T-butyl, tert-butyl. There you go. So those are all the groups that you should know. You should know all of these different substituent groups. The other ones that are important are the halogen groups, and all of those end in O. Fluoro, chloro, bromo, iodo. But they're not just atoms by themselves. They are joined on to other chains. Nitro is the other group that's good to know, NO2. Alright, so going back to our original problem. 3-methyl, 4-N-propyl hexane. So we know we've got a methyl group hanging off the 3. If we go back down here, you can see what these look like when they're hanging off the base chain. A methyl group is just going to look like a line. An ethyl group just looks like a line with another line on it. And propyl looks like 3 like this or 3 like this, depending on whether you're dealing with isopropyl or N-propyl. We're dealing with methyl and N-propyl. Right, so we've got a methyl group hanging off 3. So there you go, 1 carbon hanging off 3. And it says an N-propyl group hanging off 4. Then we need 3 carbons, like that. And this one's N-propyl, so it's hanging off the end carbon of that substituent group. Alright, so that one's complete. Let's take a look at a cyclic compound. In the case of a cyclic compound, the base chain is a cyclic unit. And we can tell what the name of a cyclic unit is because it has the word cyclo in front of it. Cyclopentane would be a cyclic unit consisting of 5 carbons, because pentane, the base chain, has 5 carbons as well. So if we were drawing line structures, it would look like this. Look like a pentagon, actually. There we go. Now when you're numbering a circle or a cyclic unit, it doesn't matter where you start numbering. You can start numbering here, 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 here. It doesn't matter. It's all the same. So just start numbering somewhere and number all around the ring. Now the name on this one is 1,3-dimethyl cyclopentane. So what that means is I've got a methyl group hanging off the 1 and a methyl group hanging off the 3. And that would be that structure completed. The di part means there must be 2 methyl groups hanging off the ring. So you've got these prefixes: di, di, which is 2, tri, which is 3, and tetra equals 4. And those are pretty much the only ones you really need to know. But if you got 2 of the same group, it's going to be di, 3 of the same is going to be tri, and 4 of the same is going to be tetra.